Joel, can I ask you to put this into dark mode, actually?
I can try.
Let's try that.
All off.
Yeah, it's okay.
Okay, now we have Dylan talking about TNG50.
Great, so thank you very much. Yeah, I'm very excited to tell you a bit about what we are very interested in these days, which is the new TNG50 simulation. But first, actually, I want to share an interesting result with you on something I'm not supposed to be talking about. So this is oxygen 6 in the circumgalactic medium of low redshift galaxies. So if you are interested in CGM, the next 3 or 4 minutes are for you. And very quickly, in one slide, I want to try to prove to you that the answer to this question is yes. And I'm going to do that by flashing a number of simulation results very quickly. So first, this is Ford 2016 from kind of pre-Mufasa type simulation. So this is equivalent width of oxygen 6 in the CGM as a function of distance away from the galaxy. So COS halo survey data in white, the models in red and blue, which are both about an order of magnitude too low. Below the data. This is Gutke 2016 from the Ni-Hao simulation, small galaxies, bigger galaxies. Again, the models below the data. This is Liang, Zoom simulation here below the data. Hummel's 2016, or 2013 rather, sorry. Variations of feedback models in even the high feedback case, again, a bit below the observational constraints. This is Suresh 2017. This is from Illustris, so this is a column density distribution function, not versus radius. Again, the model is a bit below the data. And Oppenheimer 2017, this is from Eagle simulations. Again, the simulation is a bit below where the data wants us to be, which is to say that modern hydro simulations in the past 5 years or so have had significant trouble reproducing the large amounts of O6 observed in the CGM of low redshift galaxies. So I want to show you our comparison here in this space. I want to step you through it, what exactly we do. So a survey like COS Halos has, observed, about 40 foreground galaxies and the amount of oxygen 6 around them. And so for each observed galaxy, what we do is we go into the simulation and we pick an analog matched in observed properties. So stellar mass, star formation rate, or color, environment, or isolation criteria, and redshift, sampling within the allowed error bars on each property of that observed galaxy. Then we go and we actually measure the amount of O6, so the column density, at the impact parameter as was observed from that galaxy. We repeat that procedure about 100 times. This is what I'm showing here. So O6 column density, function of distance away from the galaxy. These 3 big circles are 3 COS halos data points. And each is matched with about 100 little squares, which are the 100 Mach analogs drawn from the simulation. So the observational points are repeated over here with their error bars, and the simulated data points form these distributions, a predicted PDF of how much O6 we expect around that specific observed galaxy. So we do that for the entire full sample, and we want to then come up with some statistic, right? We want to know how do these predicted curves compare to each of the observational data points. We basically just do a p-value. So we integrate the area under the curve times 2, or the area under the limit as appropriate. So if this value is about 1, this indicates good agreement. If this value tends towards 0, that indicates significant tension with the observations. So we do it on the new simulations. The average value is about 0.5, indicating no significant statistical tension between the observations and the simulations. But if we repeat the exact same analysis procedure on the original Illustris simulation, the value is about 0.09. This means significant tension kind of at the 2 sigma level between the observations and the simulations. The point here is that the new simulations seem to be fully consistent with the low Z O6 data. I want to show you that again in a kind of a different space. So this is the covering fraction of O6 above some column density limit, again distance away from the galaxy here. So this is an entirely different data set, something called the eCGM survey, but what we've done is exactly the same procedure. So we've created 100 Mach realizations of the entire observational survey and used them to draw these lines, which should be compared to the points of the same color. And the agreement is quite nice, particularly since what they did and what we simply copied was a split into these star-forming and quiescent subsamples, indicated in the blue and the orange, and the simulations nicely following the different radial trends of O6 covering fraction between these 2 populations. Okay, so one other point about O6, and I want to focus, to tell you that I want to focus on halos of 10 to the 12 solar masses. This is a very interesting halo mass regime. It's where we have both blue and red galaxies at the same time. So here I'm showing you redshift 0 face-on blue galaxies. These are what TNG galaxies look like. They're all in halos of 10 to the 12. I'm going to flip to a bunch of red galaxies at exactly the same mass. So what you see is, of course, or a transition of morphology. It's the most important difference. There's a number of red spheroids at the same mass. But let me zoom out here and show you the O6. So zoom out by a factor of 10. I'm showing you the O6 column densities on the scale of the virial radii, indicated by these little circles, if you can see them. So this is the blue galaxies. So around blue galaxies, large extended O6 halos are ubiquitous, and they're at high column density. But let me flip to the red galaxies, again at the same mass. So this is the O6 around the red sample. I think you can see by eye a substantial difference, right? That there's a substantially suppressed amount of O6 around the red galaxies. That's just what I'm quantifying here. So O6 mass in the halo is a function of galaxy color from blue to red, left to right, at fixed stellar or fixed halo mass, doesn't matter. The trend is what we see is that through the kind of star-forming maze sequence of color, the O6 mass is roughly flat, but then it falls off this cliff. So red galaxies are strongly suppressed in their O6 content relative to what they should have had if they were still blue and star-forming. And the culprit of this is actually the supermassive black hole feedback in the simulations, with two very important related effects. So first is that the black hole feedback is actually pushing oxygen mass out of the halo to larger distance. The second effect is that the black hole feedback is also modifying the thermal state of the halo gas, making it slightly hotter, pushing the oxygen out of the O6 phase. So that was extremely fast, but the 2 points are to remember that it seems for the first time that these new simulations reproduce the O6 observations, and I think it's going to be very important to understand why that change came about. Secondly, this correlation between the amount of O6 in star-forming versus quiescent galaxies, and that the fundamental culprit of this is the black hole-driven outflows. So that was very fast, but what I'm supposed to be talking about today is TNG50. So let me kind of switch over and tell you a bit about this new simulation, which we're pretty excited about. So Illustrious TNG, of course, is our follow-up effort to Illustrious, the original Illustrious simulation, an updated physical model and a much expanded scope. So this is a family picture of the project, so to speak. It's made up of these three flagship volumes. They span a range of volume increasing to the right, resolution increasing to the left. In the middle, TNG100, this is our Illustrious redo, so to speak. It's the same box size, same resolution actually. Well, it's the same initial conditions, basically, but with the updated model. TNG300, this is our large volume effort, 20 times larger volume, 8 times lower mass resolution. This gives us a huge statistics and a really nice sampling of massive objects, 300 clusters above 10 to the 14 halo mass. TNG50 here is what I want to talk more about. In particular, in the tagline is a cosmological volume at zoom resolution. That's the advertisement, so to speak. So numbers for those that are interested. In particular, I just want to draw your attention to the mass resolution in the baryons. So TNG100 or Illustrious, this is 10 to the 6. In TNG50, it's 8 times 10 to the 4. Spatial resolution, say in the collisionless component, the stars or the dark matter, it's coming down from 750 parsecs in Illustrious to about 300 parsecs in TNG50. So it's 15 times the mass resolution or 2.5 times the spatial resolution of TNG100. It's roughly equivalent to the Auriga main sample, if you're familiar, but of course it's still about 10 times lower mass resolution than state-of-the-art zooms nowadays. So it's run on this beautiful computer called Hazelhen in Stuttgart. It's been running on 16,000 cores, which means every day we burn about 400,000 CPU hours. And this has turned into a bit of a Herculean effort. So effectively, we've been running it 24/7 for approaching a year now, and it's still running, but rapidly approaching Redshift 0, we hope. So this is a project led by myself in collaboration with Annalisa Plepic at MPIA, of course in collaboration with Volker Springerl and the whole TNG team. And just to reiterate what these TNG simulations are, so TNG50 incorporates entirely unchanged our new model for galaxy formation physics with 3 fundamental things to keep in mind. So all the new runs include MHD, the treatment of magnetic fields. We have this new AGN feedback in the low accretion state. This is this kinetic feedback mode, and a substantially revised treatment of galactic scale winds driven by supernova energy. So why, of course, why are we doing such a box? There's 3 main drivers. The first is the volume. So we want to have the volume. We want to be able to make statistically robust statements about entirely unbiased and large populations of galaxies. Second is the resolution. We want to push the kinds of models we use in these simulations to their limit. We want to push into the internal structures of galaxies. And third is Redshift 0. So this is not a reionization project. It doesn't stop at redshift 6. For us, that's only about 1% of the computational effort. In fact, we want to get to redshift 0, as we always do, to make the strongest possible connection to the observational data. There's a few key science drivers. Dwarfs, of course, there are lots of dwarfs. Thank you. There's 20,000 resolved galaxies above 10 to the 7 M star already at redshift 1. Groups and Milky Ways, there's about 100 of each. There's one beautiful cluster. It's going to be about 10 to the 14 at redshift 0, a Virgo analog, and looking at the fine-grained structure of the gaseous and stellar halos. So let me show you the dwarfs just in terms of the redshift 0 stellar mass function, the usual thing. The data is in white. The realization of the fiducial model is this orange curve. But of course, being very aggressive in resolution, we can only really push down to 10 to the 8 and something like illustrious. That's being very aggressive even. And this is not really getting into the regime even of the classical dwarfs of the local group, say. Of course, TNG50, we simply push this a bit to the left, and we can push into a more interesting regime for small galaxy studies. In terms of the groups and the bigger objects, this is getting into the internal structure of galaxies. So I'm just picking out a nice, pretty example, redshift 1, some big disk. This is a stellar light Mach on the left, a gas density projection on the right. The only point here is that it looks nice. It looks like maybe what you would expect from a zoom simulation. But we're not picking specific objects. Of course, that's the whole point. So although we have big disks, we have other crazy things going on as well. So this is some very strange orbital configuration, some merger. This is going to be a proto-elliptical, no doubt, very soon. And not just one or two galaxies, of course. Because we have the volume, we have lots and lots of statistics and examples, which is to say quite a few, and indeed a lot. So 500 or so samples here, mass ordered from the BCGs of massive groups all the way down to what I call very small dwarfs, 10 to the 8 M star or so, sampling not only the full mass range, right, but also the full environmental diversity and diversity of assembly history and evolutionary pathway all at once, all in the same simulation. Of course, quantifying some of the structure we see here is a big part of where we're going. So I want to show you just one thing, looking at galaxy structural properties. Of course, we're interested in sizes, shapes, morphologies, kinematics. This is something being led by Elise Plepich, and I'm just going to show one thing motivated by something we've already heard about today, this fascinating observations of the fact that we have more and more prolate or elongated galaxies towards higher redshift and towards higher masses, from the Van der Waals and also more recently from Zhang going up to a higher redshift. So this is the classification scheme, right? This is just based on axes, ratios, and we're looking at these galaxies in particular that occupy that space, the prolate systems. I'm showing you just some very early results from these simulations. This is a galaxy size-mass plane, stellar size, stellar mass, moving through redshift space here. So the elongated systems are in this light blue. The disky systems are in the orange with this classification. Rough conclusion. So of course, the stellar sizes decrease towards higher redshift at fixed mass, roughly speaking. We seem to be dominated actually in this classification by the spheroidals. We have this population of the elongated or prolate galaxies appearing very rapidly towards higher redshift. This is quite interesting. And low redshift, and particularly high mass, these disky and the elongated systems appear to be two very distinct classes of objects, kind of what we see here. So that's very fast. I want to come back to this last point here. So this is the structure of the CGM and the stellar halos. So the typical problem here, of course, is that we're always resolution starved in the halo. We have very good resolution in the galaxy, a very crappy resolution out in the halo near the virial radius. But of course, we crank up the resolution. We're just naturally improving this situation, resolving CGM better and better. But not just the CGM itself, but also gas processes happening in the CGM, like stripping. So I was just looking for a cool example. Looking through the groups, I found this guy, redshift 1. So this is the center of the group. This is the virial radius. This is a huge disk satellite coming in, falling. So this will be a spectacular merger in a few 100 million years. But for now, of course, you just see all this stripping material getting stripped off this disk as he's falling in. And of course, as this whole process is happening, these galaxies have some very vigorous feedback going on. Every simulation talk needs a movie. So this is my excuse to show something about the outflows which are happening in this simulation. So for those who've been following me around at conferences, this is a new movie, so you can pay attention. This is for Joe, if he's still here. This is showing you the velocity field of the gas. From 0 to 1,000 kilometers a second, that's the color bar. Here we're passing redshift 4. There's this really interesting forming object down here. You can see, actually, if you look, these kind of gently expanding flows of material. This is the winds from the stars, and then the black hole turns on. So this is our very efficient black hole feedback, turning on as the galaxy passes a stellar mass of 10.5 or so, driving this outflow to 100 kiloparsec, even megaparsec scales, driving energy which shocks into the halo gas, thermalizes. There's another very nice example, which will pop up over here just a second, as his black hole will drop into a lower accretion state and transition into this very effective feedback mode. Here it goes. You see these kind of repetitive cocoon structures kind of being blown out. And I want to draw your attention to the collimated nature, shall we say, the bipolar nature of the outflow being pushed away from this little disk, which we'll come back to in just a second. I want to let this movie get down to a little bit more redshift, where I'm just going to fade away from the gas velocity field here and actually show you, I hope, maybe here, the stellar distribution, so a stellar mass projection. This is forming a BCG of a big group, just really showing you the beauty of hierarchical assembly, all the fine-grained structure we have in the stellar halo of this object, stripped satellites going through. There's these shells of shell structures moving outwards, kind of coasting. There's these beautiful disks that kind of coast by undisturbed, and then tidal features, all kinds of beautiful stuff. So I think I have about 60 seconds left. I want to give you a few very compact points about the outflows in these simulations. The philosophy to keep in mind here is that despite the simplicity of the models that we use for feedback in these kinds of large volume simulations, simplicity at the scale of the energy injection, actually the outflows that we see have amazing complexity and interesting features in their emergent properties. So, point one, the outflows are not isotropic. They have preferred directions. So this is outflow rate. So yellow means lots of gas flux going out. It's a function of angle, galactocentric angle, and distance away from the galaxy. So I marked the minor axes with these two lines. If we're thinking edge on, the minor axes, of course, up and down. Galaxies have a preferential collimation along the minor axes. This is strange or interesting because the energy injection is entirely isotropic. So this is a natural collimation, hydrodynamical collimation of the outflow that we're seeing. Point number two, the outflows are multi-phase. So outflow rate, again, is a function of the temperature of the gas going out. Each line is a stack of mini systems going up in stellar mass. Of course, the dominant trend we see here is more and more flux and outflow at higher and higher temperatures as we go up to higher masses. The temperature here is kind of tracking the virial temperature of the halo. So this is the hot phase going out. But what we see is that above some mass, this purple line, this is m star 10.5 or so, the emergence of a bimodality in the temperature distribution. So this cold peak comes up as the black hole feedback kicks in. And actually, this is direct ejective feedback. So this is the ISM of the galaxy getting thrown out of the galaxy itself. One more point, the velocities of the outflows. So these are the stellar outflows here at low masses, a few hundred kilometers a second. Then the AGNs kick on. We see the emergence of this super high velocity tail out to thousands of kilometers a second. And the different phases move at different speeds. So this is the velocity as a function of temperature. The cold gas is down here. The hot gas has a different kinematic signature. Those are very fast points. Of course, the direction we're going here are very strong connections to the observations, to large samples of observational data about outflows, which is something I'm very fascinated in discussing further. So this is a visual conclusion. I'll just end here by thanking the team. So of course, the TNG simulations represent a lot of work by a lot of people. I want to just acknowledge the PI of the whole project. That's Volker Springel. This is, of course, in collaboration with Lars Hörnquist. And the idea, I mean, the project has really been driven to existence, I'd say, by Elisa Plepic at MPIA and Rutger Packmore at MPA. So I'll end there. Thanks. And anyone interested in this, this is coming soon.
Questions?
Well, congratulations on this fantastic project. I'm delighted to see that you are getting a significant fraction of these elongated galaxies.
We're working on it.
At redshifts beyond about redshift 1 or 1.5 at the lower masses where they are observed.
Picking up towards high Z.
So another thing that we see, I think, very clearly in the candles observations is this phenomenon that Avishai calls compaction. This flow of gas making into the center, making a starburst, And that, again, seems to be something that we really do see very strongly in the observations. Have you seen that?
So there's a paper in prep. I think, Abshai, you have this in your inbox from Melanie Abouzi. Probably will be in the archive in a few weeks. Compaction is in the abstract, and this looks at it in the context of this TNG model. So
Answer yes.
look out for it. Yes. It's very interesting.
Ben?
Uh-huh. I don't know. I don't know. So, yeah, I don't know. We could measure it, but I imagine it's quite rapid. When we make measurements of, say, the quenching time scale, these are of order a gigayear. This is when the black holes are turning on and driving some of these outflows that you see. So I think they're very quickly disturbing both the metal mass and the thermal state, probably on timescales shorter than a gigayear.
So when the next speakers set up, one last question.
Hey, yeah. So I was looking at your outflow plot as a function of temperature and then sliced by galaxy mass.
Yeah.
And it looked like the low mass galaxies. Yeah, there you go. So are the 10 to the 8 solar mass galaxies on the right-hand plot at all?
They didn't even make it, no. So, of course, these are pure theory land units, solar masses per year, down to -3. Well, this is in bins of temperature. You have to integrate by eye, so this is not the best plot. But in these units, the blue line is not here.
So the low mass galaxies aren't driving cooler gas outflows. There seems to be a floor.
Keep in mind that what I'm showing you with the outflows, this is kind of a very high dimensional function, including the distance and the radial velocity cut for which you define an outflow. So I've just picked 2 of these here. So I'm looking at quite large distances, tens of kpc for such low mass galaxies. So perhaps closer to those galaxies, you'd see more of the signature. But we can look.
Can the next speaker come, please? We don't have a speaker?
So given there's a clear mass scale where you get these molecular outflows.
They're not
which-
well. So these are ionized. So
Oh,
I call
sorry,
them cold.
sorry. Yeah,
They
the
should be
lower
warm.
temperature. Sorry, lower
Yeah.
temperature outflows. Yeah, so this is clearly connected to the turning on of the black hole
Yep.
at a certain mass scale, and sort of related, I guess, to Ben's question. How fast, once these black holes turn on, do you get? It seems like you get quenching nearly immediately, given that pretty much all your massive galaxies are quenched, at least in the lower resolution versions of TNG. So do you get powerful outflows in star-forming disk galaxies as well? Do you get AGN in star-forming galaxies that are able to drive outflows for long periods of time without quenching?
So we have, in star-forming galaxies, we have high luminosity black hole feedback, quasar mode, if you want to call it that. In our model, that does not do very much. So in star-forming galaxies, the outflows are being generated by the supernova energy, not by the black holes. And the black hole-driven outflows, how we do it in the context of this model, only occur at low accretion rates of the black hole, so they only occur above a mass threshold, stellar mass 10.5, 10.6 or so. The quenching is extremely rapid. This is true. So what we found and what we think is basically necessary to match the turnover past the knee of the stellar mass function, stellar mass-halo mass relation, past the peak is an extremely rapid quenching, near instantaneous, if you want to call it that. That's the only way to do it. There's no other speaker, so go near. Yeah.
So I suggest that we switch the order of the last 2 speakers and we continue with Sukanya. So while she's setting up, one more question. I don't know who was first, sorry.
Sandy, take it. Oh. I can take 2.
I will yield to Sandy, sorry.
Since you like your outflows, what is your,
I think they're cool.
what is, what you think they're, what does your black hole standing look like?
Just to be clear, so I have no conception that our outflows are reasonable at all. So I don't think I don't think any simulation like this has ever actually compared the properties of the outflows. So we always just compare the properties of the galaxies, specifically the stellar properties, now more and more the gaseous properties, but actually comparing the outflows themselves is a really cool new frontier, I think. But they could be entirely wrong. I don't know.
Have you looked at black hole scaling laws?
Just the usual black hole M bulge, black hole M star. Is this what you mean?
Yes.
Let's talk more.
Okay, so now with the updated program, we move to Sukhana.